Okay, in this video we're going to look at the idea of what is known as the NZ plot. And the key question for today is, how does the Z, which is the atomic number, which is the number of protons in the nucleus, vary with N, which is the number of neutrons in the nucleus? And we're going to look at this for all the known elements, and we're going to look at a graph. Graphically, this leads us to a deeper understanding of alpha and beta positive and beta negative decays. So this little bit here, how does this variation link in with the stability of the nuclei? And graphically you will see how this helps us to understand what's going on. So this is the basic NZ plot. If you look at the graph, I've got neutron number up the y-axis, and I've got proton number along the x-axis, and neutron number has got the symbol N, proton number has got the symbol Z, and if you remember from the previous videos, the mass number would have the symbol A. The blue dots you can see are particular isotopes. So if we plot particular isotopes, we haven't plotted all of them obviously, but if we've plotted a good bunch of them, you will see there's some trends, and you can see the general shape of this line. The first thing to note is that for light isotopes, all the stable nuclei follow the straight line, and what we mean by the straight line is the N equals Z line. So all of those blue dots down here, all the initial plottings, the light isotopes, they're all stable and they're following the straight line where N is equal to Z, i.e. have got the same number of neutrons as they have protons. But then what happens is, as Z increases, so as the number of protons increase beyond 20, it's as if the neutron-proton ratio increases. So the stable neutrons that we've got here they don't stick on the N equals Z line. If you imagine the N equals Z line will be straight here, I'm trying to show that with my mouse. The stable isotopes are veering up towards the N axis, so there's more neutrons coming in. And the reason for this is that more neutrons are needed to help bind the nucleus together. What they're not doing is they're not repulsive. There's no repulsive force between them. They're not like the protons. So the more protons you add, you need to add in more neutrons in terms of the ratio, more of them, to help bind the nucleus together. So in order for the nucleus to be stable, we need those extra neutrons in so the strong nuclear force can grip them and keep the nucleus. So and the key idea is that when you add neutrons in, they don't introduce repulsive electrostatic forces. So you can see the stable line shifts upwards. So what we've got here is exactly the same graph. We've got more dots on it, so you can see here there's a lot more isotopes plotted, but just like the previous screen, the green area is stable. So you can see down here up till the number of protons equals 20, all of them are within, really, most of them, there's one or two maybe outliers, but all of the ones that lie in the stable area tend to have N equal to Z, and then the stability band, the green bit, veers up and sort of climbs up towards the neutrons axis. Okay, so the stable band is shown by the green region. The stable band has an increasing neutron to proton ratio, so the closer these dots are to the y-axis, the neutron axis, the more neutrons they've got in comparison with their protons. So the key bits for the exam, I suppose, is that it's straight between N equals 20 and Z equals 20, and then it curves to about Z equals 80 and N equals 120. So you can see there's a curve up to this area here. Okay, and then what we can now add on to it, we can consider where anything that's not on the stability belt, they are the unstable isotopes, and we can look at where they all are. Now this particular area, this pinky area, these are the alpha emitters. And they're beyond Z equals 60, so all the alpha emitters are large nuclei, and the nucleus is too large to be stable, so the strong nuclear force between the nucleons cannot overcome this repulsion between the protons, so they end up releasing or ejecting or emitting an alpha particle in an alpha decay. So when you put in the showing where the alpha emitters are on the NZ plot, they're in this top area here, just below the line as well. In some books you can see, but it's sort of around the top and going underneath this line as well. Then in this area, the yellow marker, which is above, so that this is above the stability line, which is closer to the n-axis, these are where all the beta-negative emitters are. And if you think about it, in a beta-negative decay, a neutron turns into a proton. So these are more likely to be beta-negatives because they've got more neutrons. Their neutron ratio is higher, so therefore there's more neutrons to be able to be converted into protons, and in that case, they're going to move towards the stability belt because they've lost a neutron and gained a proton. We'll have a look at that in a second as to the movement of isotopes when they decay. And then underneath the line, the same, we've got the beta positive emitters, the positron emitters, and these are to the right of the stability or underneath the line, and these have got more protons. So because they're proton heavy or proton rich, a proton can be converted into a neutron, which is exactly what happens in a beta positive decay, where you get a positron and a neutrino being emitted. All right, so the key idea with this is which of the alpha, beta, and beta negative and beta positives, where are they in relation to the stability line, and why is that the case, and why none of these are close to the n equals z line unless they're very small. That's the key ideas in this. Okay, and just in the last couple of lessons we've looked at this. These are the decay equations that you need to know for alpha, beta negative and beta positive, and don't forget the neutrinos on the end. Okay, so let's just zoom in on the graph, and if you imagine what we've done, we've zoomed in on a graph. I haven't, we're somewhere in the middle, so this is just the n side and this is the z side. If we did an alpha decay, so there's the equation coming up, if this particular red dot here was going to decay via alpha, then what actually happens is an alpha particle is emitted, which means the neutron number and the proton number reduces by 2. So it needs to go 2 down on the n and 2 down on the z. Okay, so what happens is that's the movement. That's exactly where that's where it moves. Now, if you think back to the previous graph, this means that it's going to move towards the stability belt because the alpha emitters were at the top of the line. With the beta negative decay, there's the equation coming up to remind you. If this yellow dot here decays via beta, then what happens is a neutron turns into a proton. So we end up with -1 on the neutron, the n-axis, and +1 on the z-axis, the proton. So you end up with a movement diagonally down towards the right to there. And if you think exactly where the beta negative emitters were, they were above the stability, the diagonally above the stability. So this is going to move them down towards the stability belt. And then exactly the same here with the beta positives. So if this blue dot is a particular isotope, if it decays via beta positive, then it's minus a proton plus a neutron, because a proton turns into a neutron. So that blue dot's going to move diagonally upwards. And if you think on the previous graph, the beta negative, the beta positive emitters, were below the line of stability. So this is going to bring them closer to the stability line. And really the key idea of this lesson is for you to go back, look at the NZ plot and consider the movement of the isotope in terms of its proximity to the stability belt, and you will then be able to see, your understanding will improve, because you will see that beta negative, beta positive and alpha, they are all moving the isotopes towards the stability belt. So hence an unstable isotope is attempting, if you like, to make itself more stable.